You will see the schematic here. Actually, this is the PV diagram. So from this PV diagram, we'll try to understand actually what is happening. We can see all four processes, 1 2 2 3 3 4 4 on. We can see this is the heat in and the heat out. So for 1 to 2 3 to 4, this is the isentropic, the compression and expansion. So that we already know. So in this question, what else we know? You can see the pressure at this point, it is given, and the volume V2, V3, V1, V4 all are just defined here. So what we need to do here in this from this problem, the working fluid is air, and we know the compression ratio, which is 18. So that's the compression ratio. We know the cutoff ratio. We know the definition of the compression ratio and the cutoff ratio. That's not the intention of this video, so definitely you already know that. Here you will see when the compression starts, at the very beginning of the compression process, the working fluid pressure is 100 kPa. So this is the initial state. The temperature is 27 degrees centigrade, and the volume is given, this 1970 centimeter cube. We will use the cold air standard assumptions. Cold air standard assumptions we discussed last week. We need to determine the temperature and the pressure of air at the end of these processes. That means this is important. We need temperature and the pressure end of each processes. That means we actually need, initially we will calculate T2, P2, T3, P3, T4, P4, this way. So then finally, net work output and the thermal efficiency and the mean effective pressure. So that's the overall, the question. We need to solve these three different problems, three different parts. So assumptions, so as usual, I will not spend some time with these assumptions. So first assumption is the air standard assumptions. So we can say that okay, here it is, the cold air standard assumptions are applicable. Okay, and we will write this cold air standard assumptions are applicable. And the second assumption is we will see the change of the kinetic and the potential energy, the delta PE, let's say it is close to 0. So that's two of our assumptions. Okay, and in this case, what we said, the first assumption is the cold air standard assumptions are applicable. So we can assume air at constant specific heat for room temperature. Okay, so if it is cold air standard assumptions applicable, then we can assume that air is it has constant specific heats at room temperature. Anyway, so if that is the case, so when we will write down the properties, so the properties, we need all the properties at room temperature. Okay, so room temperature, we know the gas constant, it is 0.287, it is kPa. We can say it is meter cube per kg Kelvin. We know the specific heat Cp 1.005 kilojoule per kg Kelvin. In the Cv, it is 0.718 kilojoule per kg Kelvin, and the Kp in the Cp and Cv ratio is specific heat. This ratio, it is 1.4 constant. So if you ask me how you got this, this is actually the table. You can see it is for room temperature. For air, we know the gas constant is this, the Cp, Cv, and the K. So here we can write it in kilojoule per kg. If you want, you can write it as kilojoule per kg Kelvin. Okay, kilojoule per kg Kelvin. When you will write down the units, then you can write it that way. So that's not a problem. So now what we're going to do, guys, we will calculate the temperature and the pressure at the end of these processes. Okay, so look at the PV diagram here. So from this PV diagram, it is clear, we see how we already defined the V1, V2. In this case, this is actually the volume change in this horizontal axis. So at this process 1 and process 4, you can see volume is not changing. So it is V1 equal V4, and we know the value of V2, it is given V1 over 18, and V3 it is equal to V2. How we got this, that we'll discuss that one. We can get it from the formula of the compression ratio and the cutoff ratio. So we discussed it during the lecture. So we'll start with the analysis now. So if we start with the analysis, then what we can say, initially we will actually calculate, we'll determine the volume at the end of the processes from the definition of the cutoff ratio and the compression ratio. So from compression ratio, let me write it down. From compression ratio, we know the formula, the compression ratio R, it is V1 over V2. Okay, so in other words, we can say it is actually we can say V2 equal V1 over R. You can ask me why you are looking for V2. You can remember we were looking for the temperature and pressure at the end of the processes. So for this 1 to 2 processes, this is actually our target process 2. So we are looking for the pressure P2 over there and the temperature T2 over there. So to get P2 and T2, we are looking for the volume V2, V3 and V4. So we look here, the V2, it is equal V1 over R. What is V1? The volume given 1970 centimeter cube, and the R, the compression ratio, it is given 18. It is given in the question. So it should be 106.5 centimeter cube. This is V2. Okay, so we got V2, the value of V2. So now, what I said you earlier, that our ultimate target is the pressure and the temperature, but we will calculate the volume for each and every the process at the end process. So we got V2. Now we will calculate V3. So if we actually want to get V3, we can use the cutoff ratio. Cutoff ratio formula, RC. The cutoff ratio, it is V3 over V2. So here we know RC, that means the cutoff ratio value, and V2 we just calculated. So now we can write it as V3 equal RC into V2. Right. So RC, the ratio, cutoff ratio is 2, and it is 106.5. So it will be 213 centimeter cube. This is V3. So we got V3. Okay. So we got V2, V3. Now we will calculate V4. If you look here, guys, once we know V1, V2 and V3, and we know from this is isentropic change. So at this point, the volume is same. So you can see no change of the volume here. So we know V1, V2, it is same. So this is 1917 centimeter cube. So that means we have got wall volume V1, V2, V3, V4. Now, for the process, when we will calculate the process 1 to 2. For process 1 to 2, if we look here, this process 1 to 2, what is the change? It is isentropic change. For isentropic compression of ideal gas and constant specific heats, if you can remember, we know this formula from previous week. We need T2, so T2 equal T1 into V1 V2 K minus 1. Can you remember, guys? I believe you can remember. We use this. If you look week, I guess it will be week 9. Yeah, so then you will get it. So now the temperature T1, what is temperature T1 in the question? Look in the question, 27 degrees centigrade. So what is 27 degrees centigrade? 27 plus 273, so 300 Kelvin, right? So put 300 Kelvin here. V1, V2, this value. What is V1 and what is V2? That means this is actually we know that value is here. So V1, V2 is same. It is a constant value, right? So it should be not V1, V2. It should be V4 and V1, 1971. V4 and V1 is same. So V1 we know 1917. What is V2? 106.5. K 1.4 minus 1, isn't it? So it will be the temperature T2. It will be 953 Kelvin. T2. It is one answer. So similarly, when it is the pressure formula, we know for isentropic compression of ideal gas, we know P2 it is equal P1 into V1 V2 over K. So P2 is P1 is 100 kPa, and similarly V1 V2 it is 1917 over 106.5, and K is 1.4. So we'll get this value is 5720 kPa. So this is the first temperature and pressure at process 2. So we need to do this same calculation for this process 3, for this process 4, because in the question it says end of each processes. So we calculated for these processes. Now at process 3, this is it was isentropic change. For isentropic change, this is the relation we know. But when it is for this process 3, what is happening, guys? Here it is a constant pressure. See this point, if you look here, this point, process 2, process 3, what is happening? Volume changing, but the pressure is constant. So for constant pressure heat addition of ideal gas, we can say here P3 and P2, it is same, isn't it? This P2 and P3, no pressure change. So we already know P2. So P3 will be same of P2. So which is 5720 kPa. We calculated it here, in the previous calculation here. So that means we got P3. But now we need to calculate T3. So we know for constant pressure heat addition problem of ideal gas, we can write it down like this. Let's say P2 V2 T2, it is equal P3 V3 T3. We know this equation. So it is for constant pressure. When the pressure is not changing, then this is true. This formula is true. So now here we know everything. We know P2, we know T2, P3, V2, V3, everything we know. So then if we substitute every value, then we will get T3, right? So it will be kind of like this. T3 equal, as P2 and P3 are same, equal, so you can cancel out each other. That will make it easier for you. So then it will be T3 equal T2 into V3 over V2. So now substitute all the value. We know T2 is 953. Okay, what is the V2? Not V2, what is the V3? V3 equal, we know 213, and the V2 we know it is actually 106.5. So it will be 1906 Kelvin T3. So that means now we have done these two, P3 and T3. So similarly, when it is for process 4, for the process 4, actually now it's again the isentropic expansion of ideal gas, right? So for isentropic expansion of ideal gas, and this is definitely constant to specific heats, so we can write it like this for processes 3 to 4. So we'll use the same relations like what we did for process 1 to 2. So we'll use the same expression for temperature and this pressure. So let's write it down here. So it will be T4, it is equal T3, V3, V4 and K minus 1. Substitute all the value. This is 1906, this is 213, this is 1970 and K is 1.4 minus 1. So it will be 791 Kelvin. Similarly P4 it will be V3, V3, V4, K. So P3 is 5720 Kelvin, it is 213, it is 1917 and the K is 1.4, so it will be 264 kPa. Okay, so that's actually the first part of this problem. So now we got all the values. You look here, this is P4, so we got P4, this is T4, that means we got the end temperature of the process, T4, P4, and we got T3, we got P3, and previously we got T2, P2, right? So we have done with the first part of this problem. So I believe you understand, it is pretty straightforward and we just need to do some lot of calculations. So now the net work and the thermal efficiency, this is really important. The net work and the thermal efficiency. So when we'll start with this part, we know actually the thermal efficiency, it is equal the net work over the heat in. We know this formula, and the net work, it is the heat in, the difference of the heat in and heat out. So if we really want to get this, then we need to calculate the heat in and heat out at first. So from this we will get the net work, and then we will use this expression and we will get the thermal efficiency. Right guys? Yes. So in this case, actually, if we know the formula for heat in. So heat in actually happening here, this 2 to 3. That means we can say it is, we already know the formula, so I'm not actually writing it again and again. Okay, it's due to the the enthalpy difference. So in this question, usually when we solved some other problem, we wrote it as H3 minus H2. But in this problem, and it was for unit mass. In this question, it didn't mention whether unit mass or not. So we actually need the mass. So M H3 minus H2. Or if we convert it, we know the formula. We can write it as the mass, the specific heat, and T3 minus T2. I'm not going to drive this equation here again. Similarly for heat out, it is heat out is happening for this process 4 to 1, so it is something similar. It is mCV and T4 minus T1. Now you will ask me why it is CV and why it is CP. For Q output you said that it is constant volume. For heat in you said constant pressure. Look carefully, this is the heat in this process. The pressure is not changing, that's why it is constant pressure. But here actually the volume is not changing, the volume is constant. So this is CV. I believe you understand. So now let's calculate. At first we don't know the mass, so calculate the mass at first. Okay, so we can calculate the mass by using this formula. We know when we need mass, then the formula is PV equal mRT. We know the gas constant and the ideal gas equations. So instead of this, we can write it as P1 B1 mR1 mRT1. Sorry, mRT1, not R1. So P1, if we consider this process 1 like this, so then the M, it will be P1 V1 and R T1. So P1 we know the pressure is 100, V1 is 1917, it was centimeter cube. So if we convert it into meter, then it 10 to the power minus 6 meter cube. Gas constant is 0.287, and it is 300 Kelvin. Actually here for the gas constant we are writing this unit, we can say 0.287 kilopascal into meter cube over kg per Kelvin. Okay, and the temperature T1 is 300 Kelvin. So if we simplify this, we'll get the mass is 0.000223 kg. So this is the mass we got. So once we have this mass, we know the value of the Cp is, specific heat, we know the all other temperatures. So the heat in from this formula, what it will be, mCp T3 minus T2. M is 0.00223. Cp, we got it is 1.005 from the table. We write it down at the very beginning, and the temperature difference is, it is 1906 minus 953. So this value we will get it is 2.136 kilojoule. This is the heat in. Okay, we have got the heat in. Now the heat out formula, we write it down. It is mCv T4 minus T1. Cv because it is for constant, the volume. So mass is 0.00223. Cv is 0.718. T4 we got 791, and T1 is 300. So it will be 0.786 kilojoule, the Q out. So that means we know Q in and Q out. So then the net work, it will be Q in minus Q out. So it is 2.136 minus 0.786. So it will be 1.35 kilojoule. So this is the net work, okay, done. So then the thermal efficiency formula, just use the net work over the heat in. So net work is 1.35 kilojoule, heat in is 2.136 kilojoule. So it will be 0.632 or 63.2%. So this is the thermal efficiency. So we need to do a lot of calculations, but it is not complicated. So now the third part of this question, if you read, I believe you have the question with you. It asked about calculate the mean effective pressure. So this is the third part of this problem. Okay, the mean effective pressure. Mean effective pressure. For mean effective pressure, we know the formula MEP. It is equal the net work output over the maximum volume over the minimum volume. The maximum volume over the minimum volume. This is the formula for mean effective pressure. So we know the net work output. What is the maximum volume? What is the minimum volume? The volume is maximum here at these positions. You see, if we go this way, if we go this way, then the volume will increase. So the volume at this position, it is maximum. So that means the volume is minimum here. So at this position, volume is minimum. At this position, volume is maximum. So we can say V max, it is actually V1, and V minimum, it is actually V2. So what do we know? The MEP, the maximum effective pressure, it is the net work done Vmax minus Vmin, right? So in other words, we can say it is net work output, it is V2, sorry, it should be net work is maximum is V1, it is V2. So net work is 1.35 kilojoule, V1 is 1970 minus 106.5, and we'll convert it into meter cube. So 10 to the power minus 6 meter cube, and we can convert the okay, let me write it down this way, then you'll understand it clearly. So because we're going to convert the unit, yeah, so I'll write it down like this way. So it is 1.35 kilojoule, and we have got it is 1917 minus 106.5 into, let's say it is 10 to the power minus 6 meter cube. We converted it into meter cube. So 1 kilojoule equal, we know it, we can write it as 1 kPa into meter cube. So that we can do it we just, if we convert into the unit. So now if we simplify this, it will be 746 kPa. Here this meter cube will gone, this kilojoule will gone, we'll have only the kPa. So that's the, because it is the pressure, so we'll get at least the pascal or the kPa. So this is actually the mean effective pressure. So what we did, we used a wide range of equations to solve this problem. I believe you understand, and we'll discuss it during the lecture again.